let's do these problems now. These ones are going to be about parts per million, parts per billion, and parts per trillion. And these kind of problems are just about unit conversions. There is no other great thing in it except for making sure that your units are in the ratio of 1 per million, 1 per billion, and 1 per trillion. Okay, so that's all it is. It's a ratio. It kind of matters what units you have, but really it's all about ratio of the units. So let's start with the first one, which is express 45 milligrams of nitrate in liters of water in parts per million. Okay, so which means parts per million means 1 over 10 to the power of 6. Okay, because that's million has 6 zeros in it. Okay, so the way I solve this problem is by trying to keep my units straight. So 45 milligrams over 1 liter of water. Okay, and since it's 1 liter of water, I can convert this to grams also. Okay, and this is going to be kilograms, but I'm going to convert it to grams in the next step. All right, so which means this is equivalent to 45 milligrams of nitrates in 1000 grams of water. Now I'm getting to the same units at least, okay, at least to the same type of unit. So then it will be easier for me to convert from one to the other and see how the ratio is working. This is going to be equivalent. Equivalent is given by these 3 lines, and this is equivalent to 45 milligrams of nitrate divided by 1000. Now this is grams. I'm going to go ahead and convert this to milligrams, because in milligrams I can then convert from milligrams to milligrams and then see what the ratio is like, which if you can see how this is going to go, in 1 gram there are 1000 milligrams. Okay, so that's my bottom conversion here. So by the time I do this multiplication, I should get into the power of 6. All right, so which means that I have 45 milligrams in 10 to the power of 6 milligrams of water, okay, 10 to the power of nitrate ions, which means that my solution is 45 part per million. Okay, so which means that in every million milligrams I have 45 milligrams of nitrate ions. That's kind of what it means. So anyhow, that's how this calculation works. I'm going to do 2 more here, as you can see. Okay, and then we'll see, hopefully we'll get this. So the next problem then is, what is the concentration of sodium ions in 0.00152 molar sodium sulfate? Now in this case we have an added issue. We have an added issue of molarity. We have an added issue of sodium, because here you have sodium ions, but here you have 2 sodium ions. So this is going to be a little bit of a calculation, okay, because in molarity sodium is given in moles per liter. Okay, and when you calculate the concentrations like this, it would be easier to calculate something that is mass by mass, or mass by or volume by volume. Try to keep the units the same, and it's easier to work with parts per million then. So let's get started. We have 1.52 times 10 to the power of -3 moles in 1 liter of solution. Now the concentration is so less of the solution, is 1.52 10 to the -3 moles, that we're going to go ahead and assume that we have a density of 1 gram per milliliter as of water. Okay, and this is for sodium sulfate. Let me go ahead and do this conversion first. Okay, that we have 2 moles of sodium ions in every 1 mole of sodium sulfate, and then let's convert it to grams right away. So we have 22.99 grams of sodium ions in every 1 mole of sodium ion. So at least now I have my units in grams over here. Then let's go ahead and convert the units for water as well, okay, because this was 1 liter solution. So I have 1000 in 1 liter I have 1000 milliliters. My milliliters has to be down here so I can cross out my units. Okay, and so let's see how much this comes out. And by the way, I can go ahead and do one more calculation right here. Yes, and that is for the density. Okay, so in 1 milliliter I have 1 grams of water. Okay, so which means that I'm going to have my mass units. Let's go ahead and cross out the units to make sure we are on track here. So moles of sodium sulfate, moles of sodium sulfate, moles of sodium, moles of sodium. Grams of sodium is what we need, so that is fine. Then let's go back to, this is okay, all right, and let's go back to the liter solution. Liter solution is liters gone over here, so now I have milliliters, and milliliters is crossed out over here, and I have grams. Okay, so now we're dealing with grams over grams. So let me go ahead and do the calculation here, and it comes out to be 0.0699 divided by grams, excuse me, I should go ahead and put the units there, grams of sodium ions divided by 1000 grams of water. So if you want to, at this point, you can do the math over here, or you can go ahead and convert this into the parts per million, okay, because if this calculation is to be done in parts per million, parts per million, okay, what's the concentration of sodium in parts per million? So if this has to be done in parts per million, I need to have a ratio which gives me again 1 over 10 to the power of 6, which means that now that I'm in my same units, I can go ahead and multiply both of these by 10 to the power of 6 and 10 to the power of 6 over here. Okay, now you can't just multiply one side, you have to multiply both sides for 10 to the power of 6 and 10 to the power 6. Or what you can do is you can do this calculation first, all right? So which will give you 6.99 times 10 to the power of -5 grams of sodium ions, because that's what this ratio would come out to be. And once you have this, then you can multiply this by 10 to the power of 6 as well, and 10 to the power of 6 at the bottom as well, okay, because that would be 1 gram of H2O at that point. So whether you do it this way or this way, it's still going to give you both the same answers, which will be then 69.9 ppm of sodium ions. Okay, so again, remember, it's a matter of getting to the right units. Okay, once you have the units that are the same, then go ahead and make sure that they are going to be in a ratio of 1:10 to the power of 6 or 9, whatever it is. Okay, so these two calculations that we did were parts per million. Now the next one here is, what is the concentration of 0.1 micrograms of chlordane in 1 liter of water in parts per billion and parts per trillion? Parts per billion is 1 over 10 to the power of 9, and parts per trillion is 1 over 10 to the power of 12. Okay, so we are talking really very teeny tiny units, okay, over here. So let's go ahead and get started for parts per billion. Okay, first let's do this one first. So again, we'll start with our 0.1 microgram over 1 liter, okay, and then the 1 liter is going to be equivalent to 1000 grams. So this, you don't have to assume anything because it does tell you it's water. So then convert to grams, okay, by density. So we're going to do that for everywhere, so I'm not going to write it again. So 1 liter is equivalent to 1000 milliliters, and then 1000 milliliters is equivalent to 1000 grams. Okay, so then once you have the 1000 grams over here, okay, then you can make that equivalent to 0.1 microgram. You can go further down because this is grams, so you can convert this into micrograms. So 1000 grams times, and then there are 10 to the power of 6 micrograms in 1 gram. Okay, so once you do that conversion, all right, you should have the same units, which is microgram and micrograms, okay, over here. So once you have that, you will have the answer of 0.1 parts per billion. And this part per billion, again, this is a ratio, and so this ratio is in grams. Okay, that's how this works. Let's do another one then. Parts per trillion. We're going to have to get deeper into our units. Smaller, smaller and smaller. Okay, all right, so again, 0.1 microgram over 1 liter of solution, which is then equivalent to 0.1 microgram over 1000 grams of water, which is equivalent to 0.1 microgram. Okay, and now I'm going to go ahead and still make this microgram, which is then 1000 times 10 to the power of 6 microgram in 1 gram, okay, of anything in one gram. So then once I have this, okay, I'm still not into the 1 over 10 to the power of 12, because as I did this calculation over here, this gives me parts per billion, but I don't want parts per billion, I want parts per trillion. So if I want parts per trillion, I'm going to take this entire thing and multiply it by 10 to the power of 3 on the top and 10 to the power of 3 at the bottom, because 10 to the power of 3 at the bottom would mean that I have 10 to the power of 3 times 10 to the power of 6 times 10 to the power of 3. So 3 plus 6 plus 3 gives me 12. Okay, that's how I get my bottom number to be the exponent of 12, which means that now I have, and we multiply this also by 1000 on the top, I have 100 PPT. Okay, 100 parts per trillion. That's what I have. So you can see that it's easier to deal with certain numbers in parts per billion or parts per million because they have such small concentrations. So it's easier to see it this way. I hope it's clear. I don't know, just try to make sure that your units are the same and they have the correct ratio. So in case of million, it's going to be 1 over 10 to the power of 6. In case of billion, it's 10 to the 9. In case of trillion, and 1 over 10 to the power of 12. That's what it needs to be.